Hello everyone. So now we are going to week 6 lecture and lecture number 4 of the course. We will continue on the previous topic, subsoil investigation, and then we will get into the new topic, footing design. So last week, if you remember, we get into the last slide was about drilling and boring, which was one of the ways to do some ground exploration. Okay. So in this slide, we explained how to uh, make drilling or boring to extract the soil, which allow for sample to be obtained from greater depths and minimize the disturbance to the ground, which one of the important advantages. And this method has some uh, disadvantages, like it needs some specialist equipment and personnel to conduct this drilling, and also the drilling is costly. Okay, and today we will continue on same topic, and we have the bore log. The bore log is like graphical representation of the soil layer, and this one will be obtained using the drilling technique. Okay, so this will graphically representing the soil profile, and if you can see the sample, so each sample has maybe different color or different colors and different textures. So each layer has different properties, and here is drilling. Okay, this one is very important. This board log is very important for design because it gives us a wide range of the properties, or wide view of the soil layers underneath the building we are designing. Okay, so this is an example of the board log, and if you can see here, we have various layers. So for example, this is one layer. So we have various layers here, and here is another layer, here another layer, and here if you can see, the color grading is pale green, color grading is red brown to brown. So here how to classify the soil using the color and texture, and this is an example of the bore log. Okay, so this is just an example, and there is two files on the course website, so you can check and find out how to interpret the results or the outcome of the bore log. And this only to give you some like overview on the topics, and we don't need to go in details in that. Okay, and then you have another techniques of ground exploration, such as some insight to testings. We have few testing techniques. The first one is called standard penetration test, or SPT. This test is more comprehensive. Sorry. So this test is more comprehensive test and give us more information about the soil. Okay. This technique is depending on that we have a hammer. This is a hammer. And we use this hammer to hit the sampler. This is called a sampler. To hit the sampler to extract the soil. Okay, and the number of blows for required penetration correlate to the strength of the soil. So we are using the hammer to penetrate the soil, and we will need number of blows to penetrate. The number of blows to penetrate the soil correlates to the soil strength. So if I ask you what happened when we have high number of blows, if we have high number of blows, this means high strength. So the higher the number of blows, the higher the soil strength. Okay, and if you can see here, this is a sample, and the sample is undisturbed sample. Okay, so this is our first test, and again here we have an example of the bore log coming out of the SPT test. As you can see here, this is one layer, and this is another layer, this is another layer. So all this data come from the SP test. Okay, and here is some definition of the testing tool or testing machinery used in this test. So we have the standard penetration test. We have the tube diameter. So this is a sampler that will extract the soil. So it has some sharp edge, as you can see here, and the hammer will be here, somewhere here, to hit the sampler to extract or penetrate the soil. So this is our sampler, and this is a hammer. Okay, the dimension of the diameter is outer diameter is 50.8, inner diameter 33, the length is 650, the hammer weight is 63.5 kilogram, the drop height is 760. N value is the number of drops or blows needed for second and third 150 penetration in the soil. So we need the number of blows to extract the soil second and third time by 150 millimeter. Okay, so this number in value, again, it correlates to the soil strength. When the number is high, this means the soil strength is high. Okay, and here is the sampler, the total view of the sampler or the whole view of the sampler, and this part is here. Okay, so now the next test or the second test we have today in the in situ testing techniques, we have the cone penetration test or CBT. Cone CBT is quite similar to SBT, but it has some advantage over the SVBT test. In this one, we have a cone. This is an example of the cone. And we have this cone sending some pulses into the soil. And this is the machinery that is used uh, to pull the cone into the soil. And this cone will have some resistance from the soil. And this machine is recording the resistance of the soil to penetration, and the resistance is correlates to the resistance of the soil correlates to the soil strength. So the soil strength correlates to the resistance of the soil. And here is an example of the outcome from the CBT test. Okay, as you can see, here is some pulses which indicate how much is the resistance of the soil. And this one is the CB test. The advantage of the CB test is that it has continuous data through the different layers of the soil. However, because you can keep pushing the cone until you want to stop. But if we go back to the SCB test, okay, for example here, we go here. If this our sampler, so this sampler will be pushed until and record the number of blows until reaching the end of the first layer. So this is layer number 1. If you want to penetrate the second layer, we have another layer, because you know the soil is not only one layer. So if we have another layer here, layer 2, so you need to set up the test again. Okay, so this means that SCB test doesn't provide continuous data of the soil layers, but you need to stop and set up the test again for each layer. Okay, so this was just a brief discussion about the two tests, the SCB test and CB test, which are two in situ testing techniques, which give you comprehensive soil exploration. Okay, the advantage and disadvantage of this two tests can be found using this link. So if you go to the link and watch this YouTube video, so you can see what is the advantage and disadvantage of the two tests. Okay, so now the next is the final or the last one. Of subsoil investigation technique, which is not very common. Which is called geophysics. As you can see, there's something like we need to put in the ground to penetrate and hit, and then measure the waves transferred through the soil vertically and horizontally, and record it using this seismograph. And using this wave, you can also have a recording of the soil layers that was hit by the waves. Okay. Anyway, this is not a common technique, so you can just know the, that it is existing, but we don't need to go in detail on it as well. The next is soil sampling. So one of the also the topic we need to know is soil sampling techniques or the soil sampling type. As you can see here, we have few samples or few techniques to get soil samples. The first one, if you remember from previous slide, it is core drilling technique. As you can see, these samples are extracted using the core drilling or it forms a bore log. And the second one is soil may be extracted from a fill from holes or bits. Okay. These samples are good samples because it is undisturbed sample. We will know this later, but this one is not good for all testing because it is disturbed samples. Okay. So now we are talking about the sampling and sampling of the soil and what is the difference between disturbed and in undisturbed samples. Okay. The advantage of the main advantage of the undisturbed sample is it preserves the in situ condition to some extent. So this is our main concern is we need the sample to preserve the in situ condition to some exist so that the test is reliable. Otherwise, the test will not be reliable because it doesn't represent the soil in the site. Okay. The undisturbed sample, we have different techniques and equipment in different situations to extract the samples. These are the commonly used techniques to extract the samples. For example, from the trial bits and hand excavated boreholes, or from rotary drilling and from cable percussion. So from the trial bit, need to cut by hand block sample similar to the example here. As you can see here, the worker tried to keep the sample very good and not disturbing it and try to cut slowly by hand to keep the properties or preserving the texture and the shape of the soil. So this can be cut by hand. The other three methods, sorry, hand excavated boreholes, rotary drilling, and cable percussion, we use sampling tables. So we are using sample tables for these three techniques. Or the other technique is cutting by hand if you are in the trial bits. Okay, so all this method is to find the or to extract undisturbed samples. Okay, here is some examples of the sample tubes used for extracting the undisturbed samples. Also, we are just having an overview on that topic, and we don't need to go in details for that one. So, for example, we have this standard U100 system, and we have plastic linear system, and we have thin wall tube. All of them are used for extracting undisturbed samples, but for different situation and different type of soil. For example, if we look at this example here, if we look at the technique, so the technique is pushing the sampler into the soil, and this will fill the soil will fill the sampler with. Sorry, I can't finish that. So this will be filled with soil. This will be filled with soil, and also we can maybe rotate during bushing. So bushing and rotate at the same time to fill the sampler with soil. And then there is an extruder some here. This extruder will help us to extract the soil from the sampler after finishing. Okay. Also, one of the difference between the both all of them using same technique to fill with soil. So, for example, the difference is here. The dimension is different. So this one is uh, wider but longer. This one is shorter but the diameter is wider. So there is as you can see, few sampling tube example we can use to extract the undisturbed samples. Okay, now if we shift to the next sampling tube, we have some more. There is another one called double tube core barrel. Okay, it has cutting bit, core lifter, and so on. Again, what is the main advantage of these samplers? These samplers minimize the disturbance of the soil samples to get reliable results. So all these samples just to get reliable results and to minimize the disturbance of the soil samples. Okay, this also the actual view of the soil sampler double tube core barrel. Okay, what is the next step? The next step is after getting or extracting the soil samples, we need to do the laboratory testing. So the next step after ground exploration is the laboratory testing. To assess its variability and deduce soil parameter, strength, flow of design, we need some testing at the lab. So testing will give us some parameters about soil classification and soil probabilities, such as flowability and particle size, for example, elasticity, and so on. And also, the third is the soil strength, which is very important in the design. Okay, some of the common tests we have is the sieve analysis or hydrometer analysis. This for particle size, if you remember. We have consistency test or Atterberg limit test. This for elasticity. Odometer tests, direct shear test, reactivity tests, which include shrinkage test, swelling test, or suction measurements. So all this testing are lab testing for the soil, and it is important, very important uh, to know the properties, and it is very useful in the design. So if we talk in depth, in more details about the first test is the sieve analysis or hydrometer analysis. What is the sieve analysis? Sieve analysis is this testing, which is to classify the soil according to particle size. And if you look here, this is how much is the difference between the size of sand, size of silt, and size of clay. So also gravel will be more than sand. So if we order the particles from big to small, so we have gravel, then sand, then silt, then clay. So clay is the smallest size. Okay. The sieve analysis is only suitable for this two because it's big enough to be done with sieve analysis. However, the silt and clay are not applicable using sieve analysis. So we use the sieve analysis tests for sand and gravel, and this is a test. So we have some different sizes of sieve. We order from the bigger size to the smallest size. Okay, and then we put the soil on the first sieve, and we have a record of the retaining percentage. Okay, so the retaining will be more than this side. So for example, if we have here, this is a side of 12 inches. So the retaining here is more than 12 inches. And the retaining here, for example, is 4 inches. Sorry, 4 millimeter. 4 millimeter. So this dimension in millimeters, the dimension up to here is inch, and so on. So we measure the retaining on each sieve, and then we have a relation log here on this curve, and here the retaining, and we have the sizes. So you have something like that, for example. So this is a sieve analysis diagram, or this is called particle size distribution. Okay, so this only for sand and gravel. So what is the technique to know the or to investigate the particle size of the clay and silt? So the one for clay and silt will be the hydrometer analysis. So hydrometer analysis will be for clay and silt. So if we look at the some details of this test, the hydrometer analysis. So again, sieve analysis, sand and gravel. Hydrometer analysis, silt and clay. These are the hydrometer itself. So this is our hydrometer, and this hydrometer is used for classifying or knowing investigation of the particle size of clay and cell. Okay. The technique of this method is we will, maybe I add another slide here. Okay, so the technique of the hydrometer analysis is we will mix the clay or salt in water. So if you look at the previous slide, so you have this testing tube, and then you have mixture of the soil and water. Second step is after some time, because we will leave the mixed soil, and after some time the silt and the clay will settle in the bottom of the tube. This is called sedimentation process. Okay, so what will happen is we'll have some clear water here, and then the soil with the mixed soil will be here, and we have some soil sedimented in the bottom here. So this clear water, soil mix, and soil. Okay. The third step will be is measuring the soil or the mixture concentration. So this is will be the use of the hydrometer. So this hydrometer will be used to measure the concentration. So the mix, measuring the mix concentration using the hydrometer over time. For example, each 30 minutes, 1 hour, and so on. So you will have a record of the soil concentration over time. So of the mix concentration over time. Okay. And using this concentration, the clay or soil concentration, you can determine the size, the particle size of the soil. of clay or silt. Okay, so is a brief explanation of the hydrometer test for fine soil, which include silt and clay. And now we can jump to the next testing, which is consistency test or Atterberg limit test. Just a second. Okay, so this testing, the Atterberg limit test, we have talked about this properties before in the soil classification, if you remember. So the test is measuring the plasticity of the soil, consistency test or Atterberg limit test. And if you can see here, so this is for elasticity of soil. And this is usually for clay or silt soil. Okay, so if we look at this diagram here or this chart, so the soil at the original state, it is solid soil, and then so the soil is in solid state first. Then when you add water, so it become semi-solid, and then adding more water, so it become plastic solid, and then adding more water, so it become liquid. Okay, so here the limit or the barrier between the liquid state and the plastic state, this barrier, the green barrier, is called liquid limit. So the liquid limit, LL, is the barrier between liquid state and the plastic state. And we have another barrier between the plastic state and semi-solid state, which is here is semi-solid. This barrier is the plastic limit. So the area, the important area for us is the plastic area. This area is limited by liquid limit from the left, sorry, from the right, and plastic limit from the left. Okay, the consistency test measuring the liquid limit and plastic limit, and if you remember the plasticity index. So we have plasticity index, which is indication of the plasticity of the soil. We have also liquid limit and plastic limit. Okay, here is a YouTube video, so you can watch it to have an idea about how the test is conducted. And if you look here, here is some just a brief explanation. This is a Casagrande apparatus, which is this one. And again, if you remember, we talk about filling this apparatus with the soil. We have to fill half of the bowl with soil, and we divide the sample to 2 quarters. Then using the handle. We rotate the handle and keep rotating it. When the soil hit this base, so the sample again trying to unite again and form one sample. Okay, and we are measuring number of rotation to become one sample again. This is the idea behind the test. Another method of testing for liquid limit or measuring the plastic limit is using the falling cone apparatus, which is we have a falling cone like that, and we have a sample. So we're trying to make the cone penetrating the soil sample and measure how many cycle also needed, how many rotation needed for the and here is the cone, if you can see here. Okay, how many rotations or how many blows needed uh, to penetrate the soil. Okay, so this is soil sample and this is the cone. We need the cone to penetrate the sample. Okay, this is the consistency test or the outer Berg limit test. And the next test is the odometer test. So the odometer test, the odometer test is used for consolidation probabilities of the soil. As you know, if we have soil layer and we have like a house or something or high, very high load, so the soil may uh, settle underneath the load. So this called consolidation. So we need to know how much consolidation expected for the type of soil. And this test can be done in the lab. So the test is using this uh, setup, and this is the machinery for the test. The setup is we have soil here, and we have two filter plate to surround the soil, and we have water pass from both sides to allow the water to get into the soil like that. And we have on top, we have loading or pressure, vertical loading or pressure. And what we will do is applying the load smoothly, okay, and measure the deformation of the soil. So when the applying the soil is compressed, so it will move, and we need to measure this movement. Okay, so the idea of the odometer test is we applying a pressure on the soil and allowing also water to be in soil. So what will happen is when you have soil and you have soil particle like that and you have water in between the soil, when you apply load on the soil, what happened to the water? The water trying to get out of the soil, so the soil will settle and consolidation will occur. Okay, and here is some diagram showing what is expected from this test. We have to the log the pressure sigma. So we have the pressure on the x-axis and the deformation delta H on the y-axis, and using the pressure. When you increase the pressure, as you can see, increasing the pressure decrease the deformation. So increase pressure, decreasing the deformation. Again, this test is for consolidation properties of the soil. And now we will move to our last lab test, which is the direct shear test. The direct shear test is one of the very common lab tests. Which give us a clear idea about the shear probabilities of the soil. So here is the apparatus, apparatus of the shear test. We have seen this before, if you remember, and here is the sketch or sketch showing the testing procedure. So we have two parts of the test, top part and bottom half or bottom part. Okay, and we have soil in this soil in this apparatus, and we are applying a shear force on this sample here. So we'll have shear stresses here, shear stresses here. So pushing from here and pushing from other side. So the soil will be under shear stress. Also, we are applying normal stress from top. So we have shear stress and normal stress applied simultaneously to the soil sample, and we will measure the shear deformation of the soil, delta L. Okay, so we will have this uh, procedure for the shear testing, and you can see the full procedure from this YouTube video here. Okay, what is expected from the test? So we will have a relation between the shear stress on XY axis and horizontal displacement delta L on the horizontal axis, so tau and delta L. And we have, for example, three levels of normal stress, sigma. So as you can see, we have, for example, test 1.5, test 2, 1 kilogram per centimeter, test 3, 1.5 kilogram per centimeter. And as you can see, when you increase the the vertical pressure, the normal stress, so increasing normal stress, increasing the shear stress. So increasing normal stress, increasing shear stress. Okay, and here we have test 1, test 2, test 3, as you can see, and we will pick the highest point or the big point of the test, so 2, and we have peak number 1. Okay, and we will create another relation or plot between normal stress sigma dash and shear stress tau on the vertical axis. For example, we have this is peak number 1, and this is peak number 2, and this is peak number 3, and we connect this with a straight line. So we will have the intersected by intersection between our curve and y-axis is C, which is the cohesion of the soil, and the slope of this line phi is the friction angle of the soil. If I ask you, what is this soil profile? What is this soil? What is the type of soil that have cohesion and friction angle? This soil will be clay or silt soil, because clay and silt have value of cohesion, value of friction. But if we have sand or gravel soil, what you expect? For sand or gravel soil, we will have, like for example, these three values, B1, B2, B3, and we connect them together. So you will notice that the intersection will be with the 0 point. So this means that for this example, C equal to 0, and we will have only a friction angle phi 1. So friction angle. What is the type of soil that has only friction angle but doesn't have any cohesion, or the cohesion is 0? This soil should be sand or gravel. Okay, so this test, the direct shear test, is very important to find the cohesion and friction angle of soil, C and phi of soil. Friction angle, C and phi of the clay and silt soil. And also important to find the friction angle phi for sand and gravel. Okay, so this test is important, and you can have a look on the YouTube video to see the details of this test. Okay, I think that's all the testing we have for the lab testing of soil, and the next topic will be the footing design. Thank you.